So following the previous idea, now we actually have more. So now we are able to character our dual optimal solution. So what does that mean? That means as long as we have solved a primal problem, then we are able to obtain a dual optimal solution directly. Okay, so this is very, very interesting result. Typically, basically it says, well, if you have a problem, if you have a linear program, you call it primal, you have an optimal solution for that. If you want to find a dual optimal solution for the dual, you don't need to solve the dual program. You don't. All you need to do is to look at your primal optimal solution and do a little bit things, and then you get your dual optimal solutions. So this again tells us that you may say that the primal and the dual problems, they are equivalent, because once you solve A, you then solve B. Okay, so let's see how to do this. Consider a pair of linear programs. If x bar is primal optimal given a basis, all right? So in that case, once we know what's the basis, what's the optimal basis, then this equation is going to give us a dual optimal solution. So your dual may have multiple optimal solutions, that's possible. But anyway, this is going to be one dual optimal solution. CB transpose, AB inverse. So the interesting thing is that this is not your first time to see this, okay? CB transpose, AB inverse, obviously you have the memory. It is part of your reduced cost equation, okay? So let's see how to understand this. Well, first, B is optimal. If B is optimal, then the reduced costs would be non-negative, okay? There are several numbers here. That's the reduced cost for all those non-basic variables. They would all be non-negative if your B is really optimal. Okay, and then let's say CB transpose would be CB transpose AB inverse AB, right? Because this is nothing but one inverse multiply the other. So if we express CB transpose in that way, now let's take a look at this particular thing. So consider the quantity y bar transpose A. So y bar is defined in this way, all right? So y bar transpose A, if you replace y bar by this one, you're going to get CB transpose AB inverse A. So here, A is a matrix that may be decomposed into AB and AN according to your basis and the set of non-basic variables, okay? So you may replace A by AB and AN. If you do that, then this multiplication becomes two parts. You have CB transpose AB inverse AB, and you have CB transpose AB inverse AN, okay? So your CB transpose AB inverse AB becomes CB transpose. That makes sense because you have this one, all right? AB inverse and AB, they cancel each other. And your CB transpose AB inverse AN becomes your, I should say, can be related to your CN transpose, right? This particular quantity is greater than or equal to your CN transpose according to this one. So that's how you get this inequality. That's how you get this greater than or equal to. And then immediately you may see that this particular thing gets to your C transpose. So what does that mean? That means your y bar, this quantity y bar, satisfies the fact that y bar transpose A greater than or equal to C transpose. So that's a condition you need for feasibility. So your y bar can be shown to be dual feasible if you define y bar in this way. And then your y bar transpose B is CB transpose AB inverse B, and you know what's that? That's CB transpose XB because this guy is your XB, right? And then it goes to C transpose X. So according to our previous condition, this immediately tells you that given your X bar with basis B, if your y bar is constructed in this way, then y bar would be feasible and having the same objective value with your C transpose X bar. In that case, you're going to say that, okay, we're going to have this particular condition, their objective values are the same, and thus they are both optimal, according to the previous one. So this can prove that y bar is optimal. So here, more precisely, we should say this is x bar and this is x bar, okay? So this pair of x bar and y bar, they have the same objective value. That shows they are both optimal and completes this proof. So next, now we are able to consider this strong duality. So now the fact that this guy is dual optimal help us to have this condition called strong duality. Consider a pair of linear programs that are primal and dual pairs. If you have x bar and y bar, if they are primal and dual optimal, then we know their objective values would be identical. Or the other way, if you know they are primal and dual feasible, and they have the same objective values, then they are primal and dual optimal. Okay? So this is an if and only if condition. Strong duality pretty much says, well, when you have two programs and they are primal dual pairs, their objective values must be identical. Okay? So the bound provided by your dual program must be tight in some sense. Okay? And if you are able to find two solutions, their objective values are the same and they are feasible, then they are optimal. So to prove this is if and only if statement, note that the first part where you have this condition and you have that condition, this implies the optimality. This has been done by proposition 3. Okay? And then let's consider the other way. Suppose that you get CB transpose AB inverse, and you know it is a dual optimal solution, right? So that means the objective value must be CB transpose AB inverse times B, because that's pretty much Y transpose B, all right? So given that, this was going to equal to the primal optimal objective value C transpose X, according to our discussions in the previous slides. So now, as long as your Y bar is dual optimal, then we know our Y bar transpose B is going to be CB transpose AB inverse B, because Y bar can be considered as CB transpose AB inverse B, all right? And that's going to be CB transpose C transpose X bar. So pretty much you would feel that everything looks so similar, because that's true, because they are all implying each other. All right, so take a look at all of them and try to convince yourself that somehow this is an if and only if statement. So pretty much this is applying to all conditions. It doesn't really matter whether you have a unique optimal solution or multiple optimal solution. You always have strong duality for your linear programs. Okay. So this has a direct implication. Strong duality certainly implies weak duality, because strong duality says they are equal. Weak duality says they are inequality. All right? So strong duality implies weak duality. Weak duality says there is a bond. Strong duality says the bond is tight, and there is no way for you to get a better bond. So that's all of this says that the primal and dual linear programs, they are equivalent. Once you solve A, you get B immediately. And this actually may be generalized to the three possible types of linear programs. Okay? So if your primal has a finite optimal solution, we know your dual must also have a finite optimal solution. Otherwise, they cannot be equal, right? So this is possible. And once your primal is finitely optimal, there's no way for your dual to be infeasible or unbounded, all right? There's no way. So suppose your primal is unbounded. Well, if your primal is unbounded, that means you may maximize your objective value to infinity. If that's the case, there's no way for your dual to have an optimal solution or to have an unbounded situation, okay? In fact, there's no way for your dual to have any feasible solution, because once you have a feasible solution, that provides an upper bound, but your primal has no upper bound. So the only possibility is for your dual to be infeasible. Okay. Lastly, if your primal is infeasible, well, then you don't really have a lot of information about the dual. You only know that it cannot be the case that your dual has a solution. If your dual has a feasible solution, there's no way that your primal has no feasible solution. So there are two possible cases. When your primal is infeasible, maybe your dual is infeasible, or maybe your dual is unbounded. Both are possible. Okay? So we may provide many examples showing you that this is true, that is true, but I don't think we need to do that one by one. All you need to do is to understand that now, because of all those strong duality things, as long as we know one condition, we know what happens to the primal, we actually have a way to predict what's going to happen for your dual according to this particular table.